Okay, so this is part 2 of our videos. We're moving on to the next page now, and we're going to still follow those ideas of exploring the two eigenvectors. I'm going to do what it's asking me to do at the beginning, which is just to draw on our eigenvectors, basically. So we're going to be switching a little bit between referring to them as eigenvectors, as well as talking about them as the kind of Cartesian equations we found. Okay, so here, that's not very good. That's meant to be y equals 2x, which represents our eigenvector 1, 2. And then the other one is y equals negative x, which is going to go down here. Okay, they're not quite going through the origin. Okay, and that was our the other part of our solution. Okay, indicate with arrows the direction of motion of any point initially on one of these lines. So if we go back to part B, we said that we chose a point on the line y equals 2x, and we found this particular solution. This is just for one point, of course. Okay, so what would happen as if we start, what was our starting point? 2, 4. So if we start at 2, 4, what happens as t increases? Well, as t increases, e to the negative t is going to decrease. It's going to get smaller because it's an exponential that has this kind of form. The eigenvalue is -1. The eigenvalue is how that position is going to change, the scale factor is going to change. So it's got a negative scale factor. As time goes on, the values are going to get smaller. So this is going to start heading towards the origin. It doesn't matter where we start on this eigenvector, the points will start to head towards the origin, even if we are the other side. If we're in the negative side, the points will start to head towards the origin. Thinking about the other eigenvector, we had, where was it? We chose the starting point -2, 2, which is up here. And we had this as our particular solution, xy equals 2e to the 5t, -1, 1. Okay, what will happen this time as t gets bigger? Well, as t gets bigger, e to the 5t will get bigger, because this is an exponential that looks like this. So as our values get bigger, as t gets bigger, our x and y values will get larger in size. So they are going to move away from the origin. And once again, it doesn't matter which side of the origin they start out, they will move that way. Okay, so they're going to move, this time the eigenvalue is 5, so that's our scale factor every time we do this transformation. Okay, so far so good. So if we choose a point, initial point that's on an eigenvector, well, one of them is moving towards the origin because it had a negative eigenvalue, and one's moving away from the origin because it's got a positive eigenvalue. But those two lines make up a tiny proportion, completely negligible proportion, of all the options out there for our initial conditions. We've got all this area that could be our initial starting points. So let's have a think about what would happen there. In that case, A and B will be non-zero. So what do you think might happen? Conjecture from the general solution the long-term trajectory for systems which are not initially on this. Well, we talked a little bit about this idea last lesson. So where's our general solution? Here's our general solution. So as t gets big, we can say that one part of our solution is going to become more important. The numbers are going to become much larger, and the other part's going to become much less. And it's clearly this one with the large positive exponent that's going to become more dominant to how the system's changing. as t gets bigger, the first part of our solution is going to get smaller and smaller, and the second part is going to get larger and larger. If they were both positive, it would be the one that has the largest exponent that would become more dominant. So what will happen then to the long-term trajectories is that as t gets larger, I'm going to say as t goes to infinity, the second part of our solution becomes dominant. So what that means is that it doesn't really matter where we start, the trajectories are going to start following that eigenvalue, -1, 1. So trajectories will move in this direction. So we can start maybe over here. I'm put a point, maybe I should do that in a different colour so it stands out a bit more, at 2, 2. So I'm clearly closer to the other eigenvalue vector at the moment. But what will happen is as t gets bigger, is the second part of the solution is going to become more important, and we'll start heading in this same direction as the more dominant eigenvalue. Obviously, if we look at time values that are negative, the converse is going to be true. The first part is going to become more dominant, and if I go back in time, as it were, and try and trace this back, it's going to be more similar to the 1, 2 eigenvector. So that's the history of the trajectory. So, as t goes towards a negative infinity, a e to the negative t 1, 2 is more dominant. If we're putting in a negative value of time, e to the negative t is going to become a large value, e to the 5t is going to become a small value. So it's going to follow this one. It's going to follow that eigenvector. And we can use this idea anywhere really on this phase portrait.